Good morning, students. I hope that you are well. Today we are going to start a new lesson, Electromagnetic Induction and Alternating Current. So first of all, we are going to see what is electromagnetic induction. So in last class we have seen magnetic effect of electric current. That is, when electric current is allowed to pass through a conductor, it produces magnetic field around the region of the conductor. So this was discovered by Christian Oyster. Later, Ampere also proved a current carrying solenoid behaves as a bar magnet. That is, when we allow current to pass through a solenoid, that solenoid is behaving as a bar magnet. So, when electric current is allowed to pass through a conductor or a coil of wire or a solenoid, it produces magnetic field. So there arises question, when current produces magnetic field, why can't the magnetic field produces current? So the reverse effect, that is change in the magnetic field, produces current. Change in the current produces magnetic field. So a reverse effect, change in the magnetic field, produces current. So this experiment was conducted by Faraday. So in this chapter, we are going to see about electromagnetic induction. In Tamil it is called as மின்காந்த தூண்டல். So before going to the main part of the lesson, in the first part we are going to see what is called magnetic flux. So magnetic flux is nothing but total magnetic lines of force passing through a given area normal to the area. Total magnetic field lines passing normal to the given area is called as magnetic flux. Suppose I am having a small area A. Through this area, magnetic field lines are passing normal to it. So these are the magnetic field lines. So the total magnetic field lines passing normal to this area A is called as magnetic flux. It is represented by pi b. So pi bb is mathematically given by integral b dot dA. So it is the dot product of magnetic field and the areal vector. So in magnitude it is given by integral b dA cos theta. B is the magnetic field, dA is the small area, and theta is the angle between magnetic field and the given normal to the given area. So if the area and the magnetic field are perpendicular to each other, so this is area, this is magnetic field. So when I find theta, theta is the angle between magnetic field and the normal to the area. So when I draw normal to the area, this drawn normal and the magnetic field are parallel, so that theta is equal to 0 degree. If it is so the case, then magnetic flux is given by pi b is equal to integral b dA cos 0. Cos 0 is equal to 1. So this is equal, magnetic field is uniform. So b into integral dA, integration of dA will give A. So it will give BA, B dot A. So this is the expression for the magnetic flux. Magnetic flux is the product of magnetic field into area when the magnetic field and area are perpendicular to each other. On the other hand, if I have an area like this is the area. I want to find what is the magnetic flux through this area. Magnetic field lines are acting in this direction. So this is the direction of the magnetic field lines. So when I draw normal to this area, this drawn normal and the magnetic field makes an angle theta. So in this case, I have pi b, magnetic flux is equal to integral b dA cos theta. So when I do integration b into integral dA cos theta, so that is equal to BA cos theta. So this is the expression for magnetic flux. So you know, magnetic flux is given in terms of Weber. So Weber is the unit for magnetic flux. So magnetic flux is obtained by the product of magnetic field into area. Magnetic field is measured in Tesla, area is measured in meter square. So Weber is equal to Tesla meter square. So this is how we can find magnetic flux of a magnetic field. Students, in this session we are going to see what is electromagnetic induction. As I already told you, Faraday attempted to produce change in the magnetic field and to produce current. So let us consider a small circuit. This circuit consists of a coil of wire connected to a galvanometer. So we are having a coil of wire connected to a galvanometer. So this is a simple circuit. Now this galvanometer in this circuit will not show any deflection. The reason is that there is no source of current. You already know galvanometer is a device which is used to detect the flow of current in a circuit. This galvanometer will not show any deflection because there is no source of electric current in the circuit. Now we are bringing a magnet. So the north pole of the magnet and south pole of the magnet. Around the region of the magnet there is magnetic field. If there is magnetic field, there is magnetic flux. Now in Faraday's experiment, Faraday actually moved this magnet close to the coil and moved the magnet away from the coil. Whenever there is motion between the circuit and the magnet, so we can do it in two ways. You keep the circuit at rest. You move the magnet close to the circuit and far away from the circuit. Or you keep the magnet at rest. You move the circuit away from the magnet and close to the magnet. In either case, we can see whenever there is a relative motion between the circuit and the magnet, the galvanometer shows deflection. So, when I move the magnet towards the galvanometer shows deflection in one direction. From the direction of the magnetic field galvanometer, we infer that there is a flow of current in the circuit. Similarly, when I move the magnet away from the circuit, at that time also the galvanometer shows deflection in the opposite direction. So whenever repeatedly there is motion in the magnet, the galvanometer shows deflection. In the second part, you keep the magnet at rest, you move the circuit. Similarly, when I move the circuit away from the magnet, or when I move the circuit close to the magnet, galvanometer shows deflection. Or in simple I can say, whenever there is relative motion between the magnet and the circuit, the galvanometer shows deflection. So what is actually happening? Whether I move the magnet towards the circuit or away from the circuit, or keeping the magnet at rest and moving the circuit, in either case, whenever there is relative motion between the magnet and the circuit, the magnetic flux linked with the circuit changes. So, when I keep the magnet far away from the circuit, the number of magnetic field lines is less. As I move the magnet closer and closer, the number of magnetic flux field lines increases. So, whenever there is change in the magnetic flux linked with the circuit, an EMF is induced. Because of this induced EMF, there is flow of current. So this method of producing EMF by changing the magnetic flux linked with the circuit is called as electromagnetic induction. The induced EMF is called as induced EMF. The current is called as induced current. This method is called as electromagnetic induction. This is one type of electromagnetic induction. We see that either the magnet has to be moved or the circuit has to be moved. This method is called as static method of electromagnetic induction. On the other hand, we are also having another method. Let us consider circuit like this. So we are having a coil of wire. This coil of wire is connected to a galvanometer. And very near to this coil, we are having another coil of wire. This coil of wire is connected to a battery through a key. So in this arrangement, I am not going to move both of the circuits. Circuit 1, circuit 2. Both the circuits are rest. Now, when the key is closed, what will happen? Current will flow through the coil C2. Because of the flow of current in C2, magnetic field will be produced. Because of the production of magnetic field, magnetic flux linked with the coil 1 changes. Because of the change in the magnetic flux to the coil 1, an EMF is induced in coil 1. Because of this induced EMF in coil 1, there is flow of induced current. Because of this flow of induced current, the galvanometer will show deflection. Similarly, when I break the circuit, that is when I open the key, current flowing through C2 gets stopped. magnetic field produced by C2 ceases out. So magnetic flux becomes 0. At that time also, the magnetic flux linked with the coil 1 becomes 0. So as this magnetic flux changes, an EMF is induced in the opposite direction. At that time, the galvanometer shows deflection in the opposite direction. So in this method, whenever I open the key or close the key, for that moment, the galvanometer shows deflection. The deflection in the galvanometer tells that there is an EMF is produced and induced current is produced. Because of this induced current, the galvanometer shows deflection. So in this method, both the coils C1 and C2 are at rest, but electromagnetic induction is taking place in one circuit. When the circuit C2 is formed or break, such a type of electromagnetic induction is called dynamic-static method of electromagnetic induction. This is dynamic method of electromagnetic induction. So these are the experiments conducted by Faraday. So Faraday actually repeated this experiment. How he repeated this experiment? By moving the magnet very slowly. When the magnet is moved very slowly, the change in the magnetic flux takes place with a long interval of time. So the rate of change of magnetic flux is low. When the rate of change of magnetic flux is low, the deflection in the galvanometer is also low or small. At the same time, when the magnet is moved rapidly, that is very fast, the rate of change of magnetic flux linked with the coil changes very fast, very high. So what will happen? The deflection in the galvanometer will be very large. So he repeated this experiment in different ways. The result of this experiment gives Faraday's laws of electromagnetic induction. So what are the Faraday's laws of electromagnetic induction? Faraday's laws of electromagnetic induction is the answer for 3 questions. When, how long, and how much. When electromagnetic induction takes place? Whenever there is change in the magnetic flux. How long the electromagnetic induction takes place? Electromagnetic induction takes place as long as there is change in the magnetic flux. So how much of induced EMF is produced? The induced EMF is directly proportional to the rate of change of magnetic flux. So if the rate of change of magnetic flux is large, at that time the deflection shown by the galvanometer is large. When the rate of change of magnetic flux is less, the deflection shown by the galvanometer is also less. So answer to these 3 questions gives the Faraday's laws of electromagnetic induction. So what are the Faraday's laws of electromagnetic induction? It is an answer for 3 questions. We are having 2 laws of electromagnetic induction. First law, whenever there is change in the magnetic flux linked with an electrical circuit changes, an EMF is induced. The induced EMF will last as long as there is change in the magnetic flux, or as long the change in the magnetic flux continues. This is called as first law of electromagnetic induction. Second law, the magnitude of the induced EMF is directly proportional to the time rate of change of magnetic flux. So these are the 2 laws of electromagnetic induction. So last class we have seen Faraday's laws of electromagnetic induction, last part. So Faraday's laws of electromagnetic induction, we are having 2 laws. The first law, whenever there is change in the magnetic flux linked with the circuit changes, an EMF is induced and it lasts as long as the change in the magnetic flux continues. This is the first law. Second law, the magnitude of the induced EMF or the amount of induced EMF is directly proportional to the time rate of change of magnetic flux. These two laws are called as Faradays Laws of Electromagnetic Induction. Next we are going to see Lenz's law of electromagnetic induction. A scientist named Lenz repeated the experiment conducted by Faraday and determined the direction of the induced EMF. So the direction of the induced EMF was discovered by Lenz. From his observation, he gave a law. This law will give the direction of the induced EMF. So what does this Lenz law states? Lenz law states that whenever an EMF is induced, the induced EMF flows in such a direction so as to oppose the cause. Once again I repeat, Lenz law states that whenever EMF is induced, the induced EMF flows in such a direction so as to oppose the cause. So here in electromagnetic induction, we are having two things. One is the cause and another one is the effect. So cause and effect. So in order to understand this cause and effect, you consider malaria fever. So malaria fever is due to the bite of mosquitoes. So mosquito is the cause and malaria is the effect. Heat and temperature. Heat is the cause and temperature is the effect. And similarly, electromagnetic induction, in electromagnetic induction, the change in the magnetic flux is the cause, the produced induced EMF is the effect. So Lenz law states that the effect always opposes the cause. So combining this Lenz law and Faraday law, we can derive expression for the induced EMF. So if we are having a coil of wire, closely wound coil of wire, let this coil consist of n turns. So this is the magnet. We are moving the magnet close and far away. So whenever we move this magnet, there arises change in the magnetic flux. Suppose if pi b is the magnetic flux linked with a single turn, then induced EMF in the single turn of the coil is given by change in the magnetic flux by time. So induced EMF is given by rate of change of magnetic flux. Since this coil is having n turn, pi b is the flux linked with single turn. So the induced EMF in all the turns of the coil is given by n into d pi b by dt. Or I can say E is equal to d n pi b by dt. So this is the expression for induced EMF as per Faraday law. So this n pi b is called as flux linkage. Flux linkage. That is the flux linkage is nothing but total flux linked with n turns of coil. But according to Lenz law, the induced EMF always opposes the cause. So according to Lenz law, induced EMF and the induced EMF is the effect, and dN by V by dt is the cause. So effect and cause are opposite to each other. So in order to infer that, we are putting a negative sign. So combining Faradays law and Lenz's law, the expression for the induced EMF is given by E is equal to minus dN by V by dt. So this is the expression for induced EMF. This negative sign signifies the effect of Lenz's law. The induced EMF and the change in the magnetic flux are opposite to each other. In the next part, we are going to see this Lenz's law is according to the law of conservation of energy. This Lenz's law is the significance or according to the law of conservation of energy. So what does this Lenz's law states? Whenever an EMF is induced, the induced EMF flows in such a direction so as to oppose the cause. Or in another word, I can say the induced EMF opposes the change in the magnetic flux. So now we are going to prove Lenz's law is according to the law of conservation of energy. So in order to prove that Lenz's law is according to the law of conservation of energy, we shall see a simple experiment. So here we are going to prove that Lenz's law is according to the law of conservation of energy. So law of conservation of energy states that energy can neither be created nor be destroyed. Energy disappearing in one form reappears in another form in equal amounts. This is called as law of conservation of energy. So we are going to prove that Lenz's law is according to the law of conservation of energy. So according to Lenz's law, effect always opposes the cause. So what is the cause here? Electromagnetic induction. When will electromagnetic induction take place? Whenever there is change in the magnetic flux. So see this experiment. So in order to produce electromagnetic induction, I have to move this magnet. When the magnet is moved towards the coil or moved away from the coil, what will happen? The magnetic flux linked with the coil changes. Because of the change in the magnetic flux linked with the coil, an induced EMF is produced. So there is a flow of induced current. Because of this induced current, the galvanometer shows deflection. Now consider, I am moving this magnet towards the coil. So when I keep the magnet at rest, the magnetic flux linked with the coil will not change. So in order to change the magnetic flux linked with the coil, I have to move the magnets either close to the coil or away from the coil. You consider now I am moving this magnet close to the coil. When I move the magnet close to the coil, the magnetic flux changes. Because of this change in the magnetic flux, there is induced EMF. Because of the induced EMF, there is flow of induced current. As per Lenz's law, this induced current or induced EMF flows in such a direction so as to oppose the cause, so as to oppose the change in the magnetic flux. That is, it is opposing the change in the magnetic flux means it is not allowing the magnetic flux to change. If the magnetic flux is not to change, the magnet should not move. Or I can say, the induced current in the coil flows in such a direction so as to oppose the moving magnet. So it exerts a force and makes the magnet not to move. So it is opposing force must be given by the induced current. If it has to give an opposing current, this opposing force will happen only when this end of the magnet acts as a north pole. So a current carrying coil behaves as a bar magnet. So the current in this coil will flow in such a direction so that it will become a north pole. So north pole and north pole will repel. Because of this repulsive force, the magnet will not move. So in order to move that magnet, I have to spend energy. I have to spend energy to move the magnet. Because I am spending energy now, I am overcoming the repulsive force and produces change in the magnetic flux. Because of the change in the magnetic flux, an EMF is induced. So if you consider in another way, suppose if the change in the induced EMF does not opposing the cause, means what will happen? It will allow the change to occur. So without spending energy, the magnet will move. So magnet will move on its own and the magnetic flux will change. And the magnetic, due to the magnetic flux, the induced EMF continues. So without spending energy, without spending one form of energy, another form of energy is produced. This is against the law of conservation of energy. So Lenz's law clearly tells that this opposing force is exerted by the induced EMF on the magnet. So I have to spend energy to produce. The spending energy to move the magnet produces induced current, and finally the induced current in the coil is dissipated in the form of heat energy. In a similar way, when I move the magnet away from the coil, magnetic flux decreases. Because of the decrease in magnetic flux, again an induced EMF is produced. The induced EMF opposes the motion of the magnet. So an attractive force must be exerted by this magnet on the magnet. So attractive force means this end of the coil must act as a south pole. So the induced EMF now flows in clockwise direction and makes this end of the coil to behave as a south pole. So it will attract the magnet. Thereby it opposes the motion of the magnet. Thereby it opposes the change in the magnetic flux. So this experiment clearly tells that Lenz's law is according to the law of conservation of energy. So without spending one energy, another form of energy cannot be obtained. So it's that whenever an EMF is induced, the induced EMF flows in such a direction so as to oppose the cause. So Lenz's law is according to the law of conservation of energy. So next we are going to see motional EMF. The EMF produced due to the motion of a conductor in a uniform magnetic field is called as motional EMF. So here we are considering a magnetic field. So the crosses represent presence of magnetic field, and the magnetic field lines are perpendicular to the plane of the blackboard inwards. So we are having magnetic field acting inwards, perpendicular to the plane of the blackboard. So every crosses represents magnetic field lines. In this magnetic field, we are having a conductor AB of length L. This conductor is moved with the velocity v. So v is the velocity with which the conductor is moving in this magnetic field. So when I move this conductor with the velocity v, all the free electrons in the conductor are also moving with velocity v. So already we have seen that When a charge moves in a magnetic field, it will experience magnetic Lorentz force. This magnetic Lorentz force is given by Fe or Fb, magnetic Lorentz force, and the expression for the magnetic Lorentz force is charge into V cross B. So this is the expression for magnetic Lorentz force. So due to this magnetic Lorentz force, what will happen? When the conductor is moved with the velocity v, every electron will experience this much of force. Due to this force, all the electron will flow in one direction. So an EMF is produced. Induced EMF. Because of this induced EMF, there is a flow of current. So all the electrons will flow in one direction and they begins to accumulate at the end B. So the end A of this conductor will have large accumulation of electron. So because of this flow of current in this conductor, an electric field is produced. Because of the electric field, when a charge is kept in an electric field, it will experience a force. This electrical force is given by Fe is equal to minus E into E. So because of this electrical force, all the electron will flow in one direction and begins to accumulate at the end A. So the end A becomes more negative and the end B becomes more positive. Because of this separation of charges, there is potential difference across the end. So this electron will continue to move until an equilibrium condition is reached. When equilibrium condition is reached, magnetic Lorentz force is equal to electrical force. So when equilibrium is reached, that is when Fb is equal to Fe, no more electron will flow towards A and makes this A to be more negative. So under this condition, a potential difference is correct. The potential difference across the ends of the conductor is obtained by equating the two forces, that is minus E into V cross B is equal to minus E into E. So here magnetic field velocity are perpendicular to each other. So when I write minus E into VB sin 90 is equal to minus E. So sin 90 becomes 1. So you will have minus E into VB is equal to EE, minus EE. So VB is equal to E. But what is E? E is equal to, or EL is equal to V. V is the potential difference. Therefore, E is equal to V by L. So substituting this value for E, we will have V into B is equal to V by L, or V is equal to V dl. So what is this V? This is the potential difference. This potential difference arises because of the motion of the conductor in the magnetic field. Hence this potential difference is called as motional EMF. The motional EMF, this can also be written as motional EMF E is equal to dLV. So it is the product of magnetic field, length of the conductor and the velocity with which the conductor is moved. So this is the expression for motional EMF. Since this EMF arises due to the motion of a conductor in a uniform magnetic field, this EMF is called motional EMF.